All right, so 6.4b today. And just a couple of facts to start out with. The rate that a radioactive substance decays is proportional to the amount of substance left. The rate that a radioactive substance, I left out the whole word substance, sorry, decays at is proportional to the amount of substance remaining. So when you have a radioactive substance, you have so many grams of it. And then what happens is particles shoot out into the air from it. That's why it's dangerous, because the particles go through your body and cause problems. But anyway, so a radioactive substance shoots particles out into the air. And then after a while, there's less of the substance sitting there. So maybe there used to be 20 grams, and now there's only 18 grams. Okay, so this is saying that the rate at which it decays, so the amount is going away, so it's decaying, is proportional to the amount that's remaining. So this is the sentence way to say it, but there's symbols that mean this. The symbols are dy dt equals ky. We've seen this before. So now we're just applying it to radioactive substances instead of just a general subject. Okay, then there's also something called a half-life. A half-life is the amount of time it takes for half of the substance to decay. The amount of time it takes for half of the substance to decay. And as a result, if half of it decays, then half of it is remaining, right? So I put that in parentheses because it means the same thing, right? If half of it goes away, then half of it's remaining. Okay, so that's called half-life. So different substances have different half-lives. Some radioactive substances, it could take 5,000 years before half of it goes away. So then the half-life would be 5,000 years. But other substances are much more volatile, and half of it would go away in 3 seconds. So it depends on the substance what the half-life is, and that's why half-life is important, because for different substances. It also tells you how volatile it is. So if it's really radioactive, really dangerous, the half-life is very short. Okay, so the half-life sorry. Better actually look. I thought I knew. Oh yes, so for radon, (222). So this is a particular radioactive substance called radon-222. For radon-222, the constant of decay is negative 0.18 when t is measured in days. For radon 222, the constant of decay is negative 0.18 when t is measured in days. And then the question is, what is the half-life of radon 222? For radon 222, the constant of decay is negative 0.18 when t is measured in days. And the question is, what is the half-life? Okay, so when it gives us the constant of decay, the negative 0.18, that's this number here, the k in this formula. So that k is called the constant of decay. So that means that we know that dy dt equals negative 0.18 y. So now we're going to separate the variables on this and figure out what the original y equation is. So I'll move the dt over and then divide the y over. So it'll say 1 over y dy equals negative 0.18 dt. So then you take the antiderivative of both sides, once you have the variables separated. And the antiderivative of this is the natural log of the absolute value of y. Antiderivative of this is just negative 0.18 t plus c. Now in this problem, what does y represent? That's what t represents. Good. So you're thinking on the right track. T is the time in days. So someone else was talking about the amount of substance there is in grams, maybe. So y is, there used to be 20 grams, now there's 18 grams. So the y keeps changing as the time goes by. So since the y represents how much substance there is, it can't be negative. You can't have a negative amount. You can't have negative 5 grams. So I can get rid of the absolute values here. I put them there because that's the correct antiderivative. But just on this problem, since y represents a positive number, we don't need those. Okay, so now I need to solve for y. So I can get rid of the ln by raising up both sides from e. So e to the ln of y will just be y, and then e to the negative 0.18 t plus c. And then usually we split this up into e to the negative 0.18 t times e to the c. So what do we need to know in order to figure out C? We need a point on the graph, right? The problem did not give us a point on the graph. So apparently they think we can figure out the half-life without knowing a point on the graph. So I'm going to make up a point, and then I'm going to convince you that it didn't matter what point I made up. So you can't just, so bear with me. Right now I'm just going to pull a point out of thin air, and you're not going to know where it came from, but then I'm going to convince you that it doesn't matter what I did. Okay, so the point that I'm going to make up is I'm going to say at the start, there's 100 grams of this radon-222. So I'm just pulling that out of thin air. I didn't get it from anywhere. And then later, I'm going to do the problem, and then I'm going to convince you that it didn't matter what I chose here. Okay, so if I have 0, 100, that means that if I put a 0 into this formula for T, I'm supposed to get 100 out. Okay, negative 0.18 times 0 is 0. E to the 0 is 1. And then I could divide by the 1 and get 100. So now I figured out that e to the c is 100. So now I can come back down here and replace this e to the c with 100. So my equation is y equals 100 times e to the negative 0.18 t. Okay, now the question's asking for the half-life. So if I started with 100, how much would I have left after the half-life goes by? 50, so I'd be down to 50. So since I'm asking for the half-life, I want to know what t would give 50. Because I started with 100, so the half-life will be the amount of time when it's down to 50. So now I'm going to set this equal to 50 and solve for the t. So then you divide both sides by 100, and you get a half. Okay, now right here is where I convince you that it didn't matter what point I made up. So let's say that instead of picking 0, 100, I had picked 0, 200. So let's say there was a 200 there instead. Then I would have put a 200 there, right? And then that would have been, e to the c would have been 200. So then that would have been 200. Everybody following okay? So then, if it started with 200, then the half-life would be when there's 100. So if I change that to 200, I need to change this to 100, right? Because half as much. So then I would stick there'd be a 200 here, and I'd stick a 100 there. Still following okay? Then if I divide it by the 200, what's 100 divided by 200? A half. So no matter what I made up, I would have ended up at this point right here, where I had a half over here. So that's why they didn't need to give me the starting amount. Doesn't matter what the starting amount is for the half-life. Now that was a lot of what ifs. Is everybody okay? Yeah.
So then do you need the plus c? Did you just put 1/2 instead of doing the plus c?
In sort of, yes. You'd have to write it down on a problem, and then, so you're looking for a shortcut, which might work on some problems, yes. So on a particular problem, let's talk about that. But I'm also teaching about other problems on this problem, so that's why it's good to go through this separation of variables, et cetera, et cetera. But yeah, is there a shortcut somewhere in there on some problems? Yes. Is everybody okay with this? Why I don't care. Oh, the other thing I want to point out is e to the c is the starting amount. So if I had put a 200 here, the e to the c would have come out to 200. So on problems like this, the e to the c is always going to be the starting amount. All right, so anyway, I got to finish this out, right? Because I still don't know what my half-life is. So I got to figure out what t is.
Your initial t is 0, more than 1.
Yes, so I said the point doesn't matter that you make up. you do want to make up the starting point, 0, comma, whatever. Yeah, that will only work because this is only going to go away if it's e to the 0. Good. All right, so now to get rid of this e, I'm going to natural log both sides. So then that'll cross out this e. So it's going to be negative 0.18t equals the natural log of a half. I forgot my negative, didn't I? Is that why you're looking at me, Madison? Thank you. Thank you very much. So then you divide both sides by negative 0.18. So t equals the natural log of a half divided by negative 0.18. So now it would be nice to know what that was, so now let's type that in. So natural log of 0.5 divided by negative 0.18 comes out to 3.851. So what does that mean? Good. It's going to take 3.851 days for half of this substance to remain. So the half-life is 3.851 days. Okay. Good. Okay, there's another type of problem in this section that's called it's called Newton's law of cooling. So for Newton's law of cooling. So this is Newton's law of cooling is about something that you're familiar with. So if you heat something up, like maybe a cup of coffee in the microwave, after you take it out, it cools down. So the reason it cools down is the heat from the coffee disperses into the colder air surrounding it, and then that cools the coffee down. Okay, so Newton worked on this and figured out how fast things cooled down. So that's what this formula that I'm about to write down is about. You can plug in the time, and then it outputs the temperature. So a certain amount of time goes by, and then it tells you what the new temperature is going to be. Okay, so here's that formula. It's T minus Ts equals T0 minus Ts e to the kt. So if you look at this, you can see why it's in this section. Because it looks kind of like this formula, right? Not exactly the same, but it's similar. It's got an e to the kt, basically. Okay, so there's a bunch of letters in here. Little t stands for the time. So that's going to change within a problem. Like, we're going to plug in 2, and that'll tell you the temperature after 2 minutes. And then you can plug in 4 to figure out the temperature after 4 minutes. So the little t changes within the problem from 2 minutes to 4 minutes. And then the capital T represents the temperature after that amount of time. So it's a little bit confusing because we have capital T's and little t's. The capital T is for temperature and the little t is for time. So these are the variables. This is what's going to change in a problem. As time goes by, it's going to cool down, so we're going to get a different temperature. Now the TS and the T0, those are specific numbers that won't change within one problem. I mean, they'll change from problem to problem, but they're constants within a problem. So T0 is the starting temperature. And TS is the surrounding temperature. So with our cup of coffee example, T0 is what the temperature of the coffee is when you take it out of the microwave, the starting temperature of the coffee. And then the TS is the temperature of the air around it. Because that's important, right? Because you all know that if you take a cup of coffee and you just put it in the air, it's going to cool down slower than if you put it in the fridge. So the surrounding temperature helps figure out what the temperature is going to be. So that's why that's in there. Okay, so for our example, we're going to have a hard-boiled egg. Is 98 degrees Celsius. So you just finished boiling this egg. So you can take an egg, stick it in boiling water. The boiling water is 100 degrees Celsius, right? And then it hardens the egg so that you can eat it. That's called a hard-boiled egg. So then you take it out, and it's still really hot because it's been in the boiling water. So it's 98 degrees Celsius. Okay, so a hard-boiled egg is 98 degrees Celsius. So you want to eat it pretty quickly because you're hungry. So you put it under some running water to cool it down. So a hard-boiled egg is 98 degrees and is put under running water. That is 18 degrees Celsius. You leave the shell on the egg because you don't want it to get soggy, right? You're cooling down the egg so you can eat it quickly. So it takes a while to cool down. So after 5 minutes, you're very patient. After 5 minutes, the egg's temperature is 38 degrees Celsius. So it's cooled down a lot, from 98 to 38. But 38 is still pretty hot. Okay, so you can't eat it till it's 20 degrees Celsius. So the question then is, how much longer will it take for the egg to reach 20 degrees Celsius? Okay, so this is Newton's law of cooling, because we've got a substance cooling down. So let's see, we got T minus, what's the TS? Temperature of the surrounding substance, right? In this case, the surrounding substance is the water. So it's 18. And then T0 is the starting temperature of the thing that you care about. That's the 98 degrees. The egg starts at 98 degrees Celsius. And then TS appears again, minus 18. And then times e to the KT. Yes?
Does it matter what it's Celsius?
It doesn't matter, but you have to be consistent. Like, this whole problem is Celsius, so everything's going to be measured in Celsius. There might be a different problem where it's all Fahrenheit. Yeah, so but that's a great question. Does Newton's law of cooling still work if you're measuring in Fahrenheit? Yes, it does. All right, so then 98 minus 18 is 80, right? And I'll add the 18 over. So we got T equals 80, e to the KT plus 18. Now we still don't have a solid equation, do we? Because in an equation you need just two variables, time and temperature. Because you want to be able to plug in a time and get a temperature out. So what are we missing still? We don't know what K is, right? K is like the C. So in order to know the constant, we need to know a point that's on this graph. We do know a couple points, actually. We know that 0 is 98, right? The starting temperature is 98. But we've already used that. We already put that there. But the other point we know that is after 5 minutes, it's 38. So 538 is the point we're going to use to figure out the K. And then after that, we'll have a solid equation that we can use to answer the question. All right, so if you plug in 5, so 80 e to the k times 5 plus 18, it spits out 38. So now I'm just using the point 538. Put a 5 in for little t, because that's time, and I put 38 in for capital T, because that's temperature. So now I'm just going to solve for the K. So we'll subtract 18, and that's 20. It's 20 equals 80 e to the 5K. Then you divide by the 80, right? So 1/4 equals e to the 5K. Then you take the natural log of both sides. So natural log of 1/4 equals 5K. And then divide by 5. So K equals natural log of 1/4 divided by 5. I don't really want to round in the middle of a problem. But also this is sometimes hard for people to think about, so let's get a decimal. If I remember right from the last period, it's negative 0.277.
Yep.
So I'm not going to use this number because this number is rounded, but it's nice to have a sense of what the K is. Like in the last problem, the K was negative 0.18. This time it's negative 0.277. Okay, so now I have a good solid equation. I know that T equals 80 e to the natural log of 1/4 divided by 5t plus 18. So this is kind of hard to think about, but that's just negative 0.277 t. Okay, so now after all that, I'm finally ready to answer the question. The question is, how much longer will it take for the egg to reach 20 degrees Celsius? So where does the 20 go in this table? Does it go here or here? It's the temperature, right? So the question is, what is the time to get to 20? So now I'm going to plug 20 in for capital T over here. So 20 equals 80 e to the ln of 1/4 divided by 5t plus 18. Then you minus the 18, so that'll give you 2. Then you divide, at this point the algebra is looking familiar, right? You divide by the 80, take the natural log of both sides to get rid of the e. So that's 1/40th equals e to the natural log of 1/4 divided by 5t. Then you take the natural log of both sides, so that's the natural log of 1/40th equals the natural log of 1/4 divided by 5t.
The division of natural logs is subtraction within the.
Sure, if you wanted to, you could rewrite this as natural log of 1 minus the natural log of 40. Yes. Then you divide, right? So that's the natural log of 1/40th divided by this number. It's about negative 0.277, right? But I'm trying not to round.
When you divide by like 83.
It's not true that 2 logs divided is 1 log subtracted. It is true that 1 log divided is 2 logs subtracted. Good. So everybody okay? So now you got to try to type all that in. And I think it's 3.8. No, that's the last problem. The last problem, the answer was 3.851. 13 point. So are other people getting that? 13.305, that's correct to 3 decimal places. Okay, good. Thank you. So what does that mean? 13.305 minutes to cool down to 20 degrees Celsius, right? Now, is that 13 minutes from when? From 0, right? So 13 minutes past when you first took it out of the water to check it. So the question says, how much longer is it going to take? So I guess we got to subtract 5 from that. Because it said we did this, and then the question was, how much longer from that? 13 is how much time it is from 0. But the question, how much longer, is how much time from this. Not that big a deal, but. So 8.305 minutes longer is our final answer. Everybody totally good? Okay, that's all for today. So you got 10 minutes to